Good morning, everyone. So last week we talked about different mapping types. So this was including stuff like tuples and lists, and I want to revisit that just really briefly and give some, I think, overview reminders of how those things work. So, when we learned about tuples, the big thing that I wanted you to take away about tuples was the fact that for tuples, you use parentheses to denote a tuple. So if you want to start a tuple, you can say something like tuple example equals and then parentheses, and this is the notation you use for tuples or what we call syntax. And if you want to do a list, you do square brackets like this. So depending on which one you use, this determines the data type. And the main difference between the two is that once a tuple is created, it cannot really be changed, which is good if you want something that is unchangeable. You can't mess with it once it's created. A list is a little more flexible. Both can be indexed. So today we're going to kind of extend off of this and talk a little bit more about other sequence types, mapping and sequence types. So starting with ranges, we're going to go ahead and open up your terminal. And remember, we can type PFG to get to the Python focus group. Now, I'm going to recommend navigating to session 7 and creating it if you have not done so already. And we are going to make a file. So we'll say ranges.py. And now I can open that up here from my file finder, and I can edit it in my text editor. Okay. So one of the really useful things in Python is a range. So a range is exactly what you would think it is. It's just a range of numbers, and it's actually stored as a list. So let's say we have a list of numbers. We can say numbers is range 1 to 6, and we're going to turn this into a list. So remember last session, we talked a little bit about typecasting. So if you want to turn a string into an integer, you use the int function. If you want to change a float into an integer, you use the int function. If you want to change something into a float, you use the float function. So typically, if you're doing any sort of typecasting, you use the name of the object. So in this case, we are changing this into a list. And so what we're going to do here is print our numbers range. So now we can run python3 ranges.py. And we see that its output is a list, again with those square brackets, because that's how we show a list. And we see the numbers 1 through 5. So again, this is that weird behavior we see where it's the starting value. So this is the very first value it's going to start at, and then it's usually the last number plus 1. So this is the number, like you want 1, 2, 3, 4, 5, so you put 6. One of the things I want to stress here is whenever I'm running ranges, I always do a sanity check to print it because I always forget this weird notation. I'm like, is it 0 to 5? Is it 1 to 6? Is it 1 to 5? Always use the print function if you're unsure. I remember a while ago, I think it was during one of the IGG classes that Titus had brought up, like, how do you trust the data? How do you trust what you're working with? And a lot of it is just looking at it. So how do you know that you're working with a list 1 through 5? You check. So similarly, if we want to print a range 1 through 20, we can say range 1, and then let's say we're just troubleshooting right now. We say we want to range 1 through 20, and we're going to turn that into a list. So we're going to flank that whole thing with list, and then we'll print range 1 through 20. So we do this and we see that it starts at 1, but it ends at 19. So this is a really good example of we wouldn't have caught that if we didn't check. So what we have to do is add 1. And now if we change it to 21, we see the behavior changes and we get 1 through 20. So this is just something to keep in mind. So now remember that when we were learning about indexing with strings, with lists, with just about anything that can be indexed, you can also use what's called the stride. So let's say we want to print a list of only even numbers from 1 through 10. So we'll say even numbers equals, and we'll turn it into a list and say range. So since we're doing even numbers, we'll start at 2. The last number we want is 11, or is 10, so we need to move it up to 11. And we want every second number because these are the even numbers. So we can give it the stride of 2. So in the prior notation, we were using a colon because that was indexing, but since this is the range function, it's taking it in as an argument. And one thing I want to show about the text editor, which is kind of fun, is here it's actually giving me some information, and there's customizable stuff. Sometimes when you're working with text editors, you can get these helpful hints and things like that. But here we see with range, there's the start, stop, and then step for the list of integers. So it tells you exactly what the arguments are that can be taken in by range. And so now if we print even numbers, we should see 2, 4, 6, 8, 10, because we told it starting at 2 and ending at 11, which is functionally 10, give us every second value. So this allows you to work with data without coding things, or without hard coding things, meaning like writing it yourself. So let's say I had a list of, I want 1,000 things going on. So I can say even numbers, and I actually want to change this to 1,000. So now I can say 1,000, 1, and now it prints a list of even numbers up through 1,000. So just like that, by adding 2 characters into our script, we were able to get massive amounts more of data. So this is why you shouldn't hard code, because if I said even numbers and said 2, 4, 6, 8, 10, and then used this is what's referred to as hard coding, meaning like it's not changeable from that point. It's not easy to change. If you want to change it, you have to rewrite it all together. So you don't ever really want to do that. You want your scripts to be written very flexible. Okay. So this is the reason I moved ranges was last time we were going a little bit over time. But we're going to actually shift gears now. So this is extending from lists, but we're going to move to dictionaries. So now we can say in session 7, touch, you can say dictionaries.py, and we can go ahead and open up dictionaries. And we can go ahead and make our first dictionary. So we can put our interpreter directive. I do want to be clear, this doesn't actually break your code if you don't have it in it. It's just highly recommended so you don't run into potential issues with language stuff. It's not strictly necessary, just good practice. So talking about dictionaries, I do want to actually share this. I'll post the link in chat again since a few more people have joined. Okay. So dictionaries are arguably one of the more helpful things in Python, in my opinion. So generally speaking, the 2 types of data storage methods I use are lists, which are like the square bracket notation, and that's usually for like one-dimensional data where I'm like, I just have one value. Like it's a list of values and I need it stored somewhere. Dictionaries are really, really helpful because you can store paired values with each other. So this means if you're doing some sort of statistics, if you're reading in information from a data frame, and I'll give a biological example in a moment, but what I mean by that is these values are paired. So you use these curly brackets to say that this is a dictionary, and you can assign a key and a value pair. So these are always paired data. So A is 0, B is 1, C is 2. So dictionaries are really nice, especially when you're working with large data. And a good example of this is actually when I was working with Nix data, I was trying to find the guide sequences and needed to maintain a counter. So I put the actual sequences as the keys to the dictionary and initialized all the values as 0. and then iterated through all of the BAM files and the data. And every time I found an instance of the guide sequence, I would just add one. So I was doing some basic math, but just searching through. So this is able to keep the information paired and kind of multidimensional at the same time. So let me switch back to it. So yeah, we'll make our first dictionary. I'll say dictionary one equals, and then we use those curly brackets. And the syntax is usually your key, and it has to be a string of sorts followed by a colon for the value. So this is the element, and then you can say, you can add as many elements as you want, really. So now we have C2. And this looks a little messy. One thing, again, going back to like Python is really forgiving with spaces and things. You can actually just do a line break here if you want. This is really common notation that people use when coding to show different arguments or different entries. So this shows us that our dictionary has three different entries. And if we print dictionary one, we see that it prints the whole dictionary. So it's printing A, B, and C. So I want to stress you can actually use lots of different data types in a dictionary as well. So mixed data types in a dictionary. So we can create a dictionary called dictionary2 and say my string. So this is some sort of string and we'll give it coffee as the value. We can give it another value and say, or another key and call it my int and give it an integer as the value. You can say my float and give it a float as the value. You can say my list. So you can even embed an entire list in this. So you can say 1, 2, 3, 4, 5. And as long as you flank it by these curly brackets, so beginning and ending with the curly brackets, you can store any amount of data in this. So you have different data types at each of these positions. So now if we print dictionary 2, we should see our dictionary gets printed. So one of the things we do with dictionaries that's a little bit different from lists is the indexing step. So lists inherently organize things by index starting at 0. So this would be index 0 is coffee, index 1 is 8, index 2 is my float, or which is 9.2. For dictionaries, we're basically giving it the index ourselves. Instead of having a 0, 1, 2, 3, 4, 5, it uses the key as the index. So if we want to find a value in a dictionary, we can go ahead. This is just copied straight from the notes. But dictionary 3, we have a car that's a Honda Civic 2020. So we have the brand, model, and year. And we can access those values. So we can say print dictionary 3, and then similar to how we would do 0 for a list, you can actually just say something like brand in the place of that. And it'll print Honda. So that is how you access the elements in a dictionary. You would actually have to use the key itself. So if you want to add a new entry, you can do so as well. So dictionaries, like lists, are not immutable, meaning like you can actually change the information in a dictionary. So we can say add new value using, or just add new values. So we can say dictionary 3, and then we can give it an actual key. So we'll add a new key, owner, and then say equals, and then we will assign whatever value we want. So we'll say add Sadie in there. So print dictionary 3, and now we see Sadie has been added as an owner in this dictionary. So you can add things, you can also delete things. So we can say delete values. We can say delete. So that del is the delete function. And then we give it the key. So owner. And then we can print dictionary3 again. And we see that there was owner and then we deleted it. So you can change the elements in a dictionary, which makes it really easy. You can also check if there's values in dictionaries. So one thing that I do want to mention about dictionaries is they are known for their speed. So unlike lists where it needs to store basically like this, so like first element, index one is second element, it needs to store the index and the element itself in a specific order. And it has to preserve that order, which means it takes more memory. In a dictionary, one thing that's kind of funky, it actually doesn't preserve the order. So by random, sometimes if you print it enough times, you'll see that the order of stuff has switched. So you'll see like model actually comes before brand. So this is really helpful when you're working with big data, specifically because all you care about is the key and the value pair. You don't care about if brand comes before model or if model comes before year. So when you're working with something that's really, really big, I'm talking like thousands of elements, and you're running into any sort of memory issues, dictionaries are your go-to. So dictionaries are really helpful for managing large amounts of data in a way that's friendly for memory optimization. So finishing up with some of the stuff in dictionaries, we can also check if stuff are in dictionaries. So this is tied into that element of speed. So checking if something is in a dictionary is actually faster than checking if something is in a list. So we can say check if elements are in the dictionary and say check one is owner. So we will check if owner is in dictionary3. So literally, it's just owner in dictionary3, and this will return a true or false. So we can say print check one, and it'll say false. And that's actually because we removed the owner. But let's say I comment these lines out where I deleted owner. Now it'll switch to true because Sadie is still the owner. So you can do this for any key that you have in the set. So you can say check2 equals year in dict3 and print check2. And this should return true because we have the year 2020. And now we're going to do final checks. So we'll say 2020 in dictionary3, print check3. And notice that this says false. But we actually see 2020 is in dictionary3. But it's returning false because we're telling it to look through things specifically at the key level. So the keys are what it's checking, which is brand, model, and year. It's not checking for the values. But we can actually access the keys and values differently. So we can say view all keys, and we can say print dictionary3, and then you use the .keys function. So .keys will give you all the keys in the dictionary. So now if we print that, we get the dictionary keys as brand, model, and year. And it tells us that these are the keys. Now we can also print the values. So we can say view all values and say print dictionary3, and similar notation, it's just a function values. So it's the .keys and then .values. And Nick had a really great question last time about object-oriented programming and the idea of classes. So in Python, things are stored as objects, and dictionaries themselves are an object. And one of the attributes about these objects, specifically dictionaries, are the keys and values. That's why instead of saying values dictionary3, it's actually dictionary3.values, because this function is specific to the data type of a dictionary or specific to the object of a dictionary. So you append it at the end. So now if we run this, we see these are our keys and these are our values. So you can access both of those elements. But again, we're going to talk about dictionaries in more depth a little bit later. Dictionaries are super, super powerful, and honestly, one of the things I probably use in most scripts that I write, but primarily in the form of like for loops and things like that, which I think we'll actually touch on next session. So we'll get to the utility of them a little later, but for now, just know that dictionaries store key and value pairs, and they're denoted with these curly brackets. That's the big takeaway for now. Okay. So now we're going to move on to another data type called a set. So we're going to say touch set types.py. So here we can open our set types. And I'm going to send the link to the markdown again, just so everyone's following. But I'm going to be copying this set here. So I'm just copying this over because it's a lot of typing. Okay, so we're creating a set. So notice in this set, we're using square brackets, which is a list, and saying Michael Jackson, Thriller, 1982, some time, a list of other things, and whatnot. So we have all sorts of things going on in here. And now we're going to turn this list into a set. So really quick, I do want to say we can print the type of album list, and I'll show you that that's a list. And we can also print the type of album set, which should be a set. So the type function is how we check the types. And remember, I was saying whenever you want to data cast or typecast something, you use the name of the item or the object as the function. So here, the set function is turning this list into a set. So now if we say Python 3 set, we see that this album list is type list, but then once we switch it to this, it's called class set. So we've switched the thing from list to a set. Why is this useful at all? I will tell you. So lists and sets are almost the same thing. The main functional difference between the two is you cannot have duplicate values in a set. So this is really easy when you're adding a bunch of stuff to a list as you're iterating through data. So let's say I'm reading in a column's worth of data to be like, oh, read all these variables in for an RNA-seq experiment, but I only need the unique group names for this. I don't need a copy of every single replicate for this thing. So if I just turn the list of those elements into a set, it will return only the unique values for me to iterate through, which is a lot more powerful than a list because I don't need to do a bunch of duplicate work. But functionally, they are almost the same thing. So similar to lists, you can add stuff. So try adding an element. We can say album set. And for lists, you use append. For sets, you just use add. So we can say back in black and then print album set. So now we should see we went from here to here and we have back in black. So this is also a really good thing that I want to mention. Um, This is similar to a dictionary. So remember, dictionaries have the curly brackets, and I said that the order is not preserved. Here we see the order is not preserved as well. We added back in black, but it added into the middle of the set, even though we didn't specify where we wanted to add it in. So this is just something to keep in mind as well. You can also remove stuff, so you can add, you can remove, so we can say album set and then remove, and we'll remove the 10.0 and we'll print album set again. So you can add, you can remove. So now notice that 10 is gone. And going back to the whole order situation, the first time we printed it, it started with pop and rock. This time it started with 65 and pop and rock are over here. So that order is not preserved. And this is actually because of a random seed that gets initiated when you run stuff. So it just kind of selects a random seed and then prints whatever order it needs to. So that's why you need to be mindful, like a list stores things in a certain index order, a set does not. It's literally just kind of a list of elements with no rhyme or reason other than it's a unique list of elements. So that sets sets apart from lists. And just like the other, like what I demonstrated with the dictionaries, we can also see if there's something in a set. So you can say verify element presence. So we can say exists equals back in black, and we use the same exact notation. We give it the element that we're interested in finding and ask if it is in the item we're querying. So in this case, the album set, and it should return a true or false, which is called a Boolean. So true or false is a Boolean value. So because back in black is in this album set, it returns true. And we can do the same thing for another element. So let's say we say we made a typo. Now it's going to say it's false. That item is not actually in the set anymore. So these true false values are going to be important later on. And as per usual, I just want you to know that these are functionalities that you can use and that we can assess the data types in this way. Once we get to more complicated stuff outside of just building up your toolbox, you'll start to see the utility of this more. So one thing we can also do with sets is find intersecting elements. So we can say, I'm still copying these items from the reader, but we have another album set here. So we have this album set, which is the above, which is the Michael Jackson Thriller, 1982, pop rock, R&B, and whatnot. And we have another set. So this is Thriller, Closer, The Queen is Dead, Born in the USA, Synchronicity. Oh, I didn't print anything. So now we can say print another album set. And we should see that this is now printing. But what if we want to see what elements are shared between the two? You can actually do that. So you can say my intersections 1 equals album set and another album set. And then you can print my intersections 1. So this and is very similar to like the probability rules, like you want to see what's in this and this element. So when we print it, it says that the one thing that's shared between them is Thriller. Another way that you can do it, it's the same functionality, it's just a different syntax. We can say my intersections 2, and instead of saying album set and another album set, we can say album set dot intersection and then another album set. And then we can print that. So we can either use this and, or we can use the dot intersection function and then put the second set as an argument here. So if we print it, we get the exact same output. So again, you can accomplish the same thing, but different ways. One of the nice things about coding. So if we can find the stuff that's intersecting between the two, it would also make sense that we could probably find the things that are different between the two, and in fact, we can. So we can say find elements unique to each set. So we'll say unique to album set, and we'll find the things that are unique to this album set. So we'll say album set dot difference. So you're basically subtracting out anything that's not in another album set. So now we can print unique to album set. And because Thriller was shared between the two, it's not going to print out here. So these are the elements that are unique only to album set that are not present in another album set. And we can also reverse this. So we can say unique to another album set, and then say album, another album set dot difference, and then album set. So depending on which one you're querying, this difference is applying the function to this object. So it will tell you what's unique to this object relative to this. So we'll say print unique to another album set. I've typed album so many times, it's starting to look like not a real word to me. Okay, so here we're seeing what's unique to another album set. So we're seeing Closer, Born in the USA, The Queen is Dead, and Synchronicity. So again, we're not seeing Thriller here. So you can find things that are intersecting, things that are unique. It's flexible in terms of storage. So going back to like dictionaries are faster than lists, sets are also faster than lists because you're not storing the index. It's just kind of a randomized index. But that also means you cannot actually index anything. So you can't access, like if I say, um, let me try something here. Say print album set. If I say 0, this should yell at me, theoretically. Yeah. Oh, that's just a syntax error. There we go. Yeah, set object is not subscriptable. So you can't really index a set like you can a list. So this does save memory, it does save storage, it does save computational resources if you need something that does so, but it does come with its limitations as well. So to move forward a little bit, um, you can join sets. So one of those things that I was really highlighting about sets is the plus side is it's all unique elements. So if you want to combine sets, you can do so, and it will still retain only unique elements. So combine sets, and we can say combined sets equals album set, and then you would say dot union. So this dot union function will join them, and then you'll say album set, and now we can print combined sets. So here is our combined set, and notice that Thriller is in here only one time. That's because sets are unique. Sets do not have duplicate values. And to really show an example of this, I want to show you the power of that by showing you duplications. So here in the list, we have a bunch of duplicate values, and we print the duplicated list. And we're going to see that it prints 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. But when we turn this list into a set, which remember we can just do with the set function, and then print that, it will retain only unique values. So now it's only 1, 2, 3. That's, I think, the biggest helpful thing about a set. They honestly aren't used much for me in my own work, other than being like, I just need a unique set of values. That's basically all I use them for. I don't really use them for anything other than I want to get rid of any duplicates. Okay. But I still want to show you guys, just in case you ever find yourself in a situation where you need more information about sets. You can assess sets in other ways as well. So we can say my subset equals, and then remember sets are denoted by the curly brackets. So we say my subset equals A, B, C. And then we'll say my superset equals A, B, C, D, E, F, G. So we can check if a set is a superset. So we can say check one, my superset. So this is my superset. And we can check if this is a superset of my subset. So basically what that means is a superset means it represents every element and more, hence the super. Subset is, I mean, I think all of you know what a subset is. It just means it's only a portion of something else. But here we would expect that since ABC is in the superset and we're asking, Is my subset a superset of my superset? We can print, check one, and we see that it's true. And that's because this is a superset of this. You can also check the other way around. So let's say we decided to switch this and say my superset. So we're switching the query this time. So we're saying, is this a superset of this? And this should now tell us false. Yeah, it's saying false 'cause it's like, no, there's actually more in my superset than there is in my subset. So this can help confirm if you're trying to subset data for querying, you want to make sure that you're not creating data accidentally or losing too much data. You can subset. I don't personally find this super helpful. You can also do the other, instead of superset, like is superset, you can say is subset. So you can go either or. You can ask if it's a superset, you can ask if it's a subset, and you can switch the query and the reference as needed. So one other thing we can do is make a frozen set. So this is just a normal set, and remember I was saying like we can add things using, where is it? We can use add, we can use remove, so we can change things around. There's also another thing called a frozen set. So we can say tuple of vowels, for example, and vowels is A, E, I, O, U, sometimes Y, but we're going to leave them out today. And we can turn this into a frozen set. So turn into frozen set. So as per usual, we use the name of the object. So frozen set, this function turns this object into a frozen set. So now if we print type of fset, we should see that the type is a frozen set. And what this means is you can't add or do anything. Like once this object is created, it's created and it cannot be messed with. So let's say we tried to do fset.add, which is the notation for adding something for a set, it's going to yell at us. Yeah, it's like there's no attribute add. Like frozen set as an object does not have the ability to add anything. Like that's an inherent property of the object. So sets and frozen sets are functionally the same. The only difference, you can't add or remove anything from a set or a frozen set. All right. One other utility is you can take things out of a set or out of a dictionary and turn it into a frozen set using the keys. So this is kind of a weird utility, but I'll show you what I mean by that. So we can say person, name, John, age, 23, sex, male. And we can say fset, and we can say frozen set person. So what this is doing is creating a frozen set from person. And this is going to grab all of the keys of the entire dictionary. So similar to what we would do by saying just like person.keys, but we can say print. Uh, we'll link this with the print function, and we'll see the output. What did I do? Oh, I didn't set it equal, that's why. Okay, just kidding. We're casting the person into a frozen set and printing that. There we go. Aha! Okay. So now it's saying that the class is frozen set, and we have the name, age, and sex. So this is telling us literally the keys in the dictionary. So that concludes our crash course of all of our mapping and sequence types. So we have tuples, lists, dictionaries, sets, frozen sets, and really, depending on what you want to do, you're going to use a different one. If you need something that's just an actual, like, one-dimensional list of items and you need it to be sorted in a specific order, use a list. If you're trying to save space and you want things that are not duplicated, use a set. If you need paired values in your data structure, use a dictionary. So just being aware of the pros and cons and kind of the attributes of each of these different objects will allow you to use them properly in your work. So we're going to switch away and go briefly to Boolean operators or Booleans, which, as I mentioned, is the true or false stuff. And that's going to be kind of how we conclude for today. So we're going to say touch booleans.py. And I'm going to, my terminal freeze. My terminal froze. I think I've been hitting too many things, so we're going to just exit out of there. Okay, so we'll open booleans.py. And now I just want to show you what a Boolean is. So in any case, it's just true or false. True, false, which is also noted as like a 0 and 1, like binary. So here, if we print type for true, it says bool. And for anyone who's familiar with R, I think R uses all capital for their Boolean. So it's like all capital true, all capital false. In Python, it's just capital or like title case. So it's like capital T, capital F, and false. And again, syntax highlighting turns it purple. So you can see if I say this, it's not purple. If I say this, it's purple because it's recognized as a Boolean. So if I do type true or false, it tells us type is bool, which is short for Boolean. So, as I said, this is kind of coded with binary where 0 is generally false and 1 is generally true. So you can actually typecast Booleans into an integer. So we can say bool2 equals int of true and say print bool2. So because true is generally considered 1, turning true into an integer should print 1. So this is where binary comes in, and you don't need to have a full understanding of binary, just generally 0 false, 1 is true. Now we can demonstrate that as well with false, so we can say false and then print bool3, and this will print 0. So true is 1, false is 0. And this is something you can cast in both directions, so we can typecast from true or false, which is a Boolean, into an integer, but you can also actually typecast an integer into a Boolean. So let's say Boolean 4 is bool 1. So the function is abbreviated from Boolean to bool, and we can say print bool 4. So if we're typecasting the number 1, an integer, into a Boolean, we would expect this to be true, which is what we get. So we return true in response. Similarly, if we change that 1 into 0, we get false. So we're able to interchange between 0, 1, true, false as needed, which provides more flexibility in the scripts down the line, especially when it comes to conditionals. Conditionals, which are honestly like one of the foundations of most languages, are like, if this case is true, then do this code, and if not, do this other code or do this other thing. So Booleans are going to become really important with any sort of conditionals. I just want to introduce it for now as an idea. So one thing we can do with Booleans is assess if values are equal. So let's say we're going to give it a list of variables and just say A is 5, B is 10, C is 5, and we'll say print A equals B. So if we want to determine if something is equal to each other, if we just say A equals, this is the assignment operator. This is basically setting A equal to B, which is not what we're trying to do. So one equal sign is the assignment operator. If you're asking the question, is something equal, you actually need two equal signs, which is kind of weird. But now we say A equals B, and we see that it prints false. But if we change A equals C, meaning is A equal to C, now that changes to true. So you're able to evaluate if things are equivalent. You can also compare the magnitude of things as well. So these are comparison operators, and it's very similar to what we learned with math. So we can say like print A greater than B. And if A is greater than B, it'll print true. If not, it prints false. So it prints false. So this is how we start to incorporate those mathematics into the data type of a Boolean, because we can evaluate these mathematic expressions as either being true or false. And it can go just about any way. So we can say print A is less than B. We can say print is A less than or equal to C. So we can use any of those mathematic terms that we used prior and evaluate them as true or false for conditions. So this is helpful for loops and conditionals later on. So now, what if I want to do the opposite? Instead of saying A equals C, what if I want to test if something is not equal to something? Well, in coding, usually to say not, you use an exclamation mark, which is kind of weird, but it's also preserved in R. So if I want to test if A is not equal to C, I can say print A, and instead of equals, we change that first equal sign to an exclamation mark. So we're saying A is not equal to C. But because they're equal, this will evaluate as false. So if we change this to B and say is if A and B are not equal, this will be true. So now it evaluates as true. So you can do this with numeric values, but you can also do this with other data types as well. So we can check if strings match. So for example, we have a section of strings. So there's hello world, hello world, hello world with some different syntax. We can check if string 1 is equal to string 2. And we see that it is. It prints true. We can also check if they're not equal, which should be false since they're equal. And now it evaluates as false. We can do this with string 1 and 3. So since string 1 and string 3 are different because this has no comma in it, it evaluates as true because they are not equal. So it's saying, yes, this statement that they are not equal is true. You can also, this is really, really weird, but you can print stuff like this. So this is A is bigger than B. And we can do this with actually anything. So let's say X and W, or yeah, W, for example. And it evaluates as true. And does anyone know why? It's a trick question. Numbers and letters are actually ASCII2 encoded. So each number itself, because of how binary storing on computers works, these numbers and letters and every character on your keyboard actually has an underlying numerical value assigned to it. And those numeric values can be used to your advantage. So you can actually compare letters like this. So you can say print A versus B. So is A bigger than B? And this is false. But is A less than B? And this is true, which means there's actual numerical values assigned to these things. So as a brief reference, these are the comparison operators. Yeah, comparison operators. So this is very similar to mathematics. It's less than or equal to, greater than or equal to. If we want to check if something is equal, we use two equal signs. If it's not equal, it's exclamation equal. And we can also use the is or is not. So I think we used some of this notation when we were looking at sets, like is this in this or something like that. So you can check like that. And now we're on our final section, which is the logic operators. So this is where we use the and, or, and not. So kind of like probabilities. So we're basically just inverting stuff. So if we say print not true, that would be false. So you can also use not, which is kind of weird. So print not true, and that evaluates as false. If we print not false, this is true. So you can use not. And one just really quick example of how this can work in an actual code implementation that's more useful than just a true or false. I'm going to show you an example of a conditional, and you do not by any means need to worry about the syntax for this for now, just to see some utility of why we care about Boolean values in general. So let's say album year equals 1983. We say if album year is greater than 1979 and album year was less than 1990. So remember, we can use and, not, and, or, which we'll learn about later with some loops. We can say print, this album was made in the 80s. So since 1983 is greater than 1979, this evaluates to true, and the album year is less than 1990, this evaluates to true. It's kind of like a truth table. So because both of these conditions, this and this are true, it's going to execute this code because we told it if these conditions are met, do this. So we say this album was made in the 80s. So now if we switch this and say like 1999, it doesn't print anything because we have not given it any instructions on what to do if that's not the case. We can do that. We can say else and then say print. This album was not made in the 80s. So this album was not made in the 80s. And now if I change that back to 1985, let's say, it'll say this album was made in the 80s. So these Boolean values, despite seeming really simple, where it's literally just like true, false, you're able to use the existence and use of this true or false to evaluate different conditions in your code. So this is really helpful because I can say something like, if this sequence is found in this file, do this set of code. And if not, do this other set of code. So you're able to identify and kind of make things, I guess, more variable, if that makes sense. Like you're able to take advantage of the actual data you're working with, evaluate it, and use it accordingly. So even if you have different inputs, you can still run the same script as long as you account for different types of inputs that you can have, which requires a Boolean. So this is your true and false. So yeah, that is all we have for today. I'm gonna pause here and see if anyone has any questions. Just a brief recap. We covered ranges, dictionaries, sets, frozen sets, and started talking about Booleans and logic operators. All right. Well, I will see you all at next section. Next session.
Just real quick, Vicky.
Yes.
We'll move the session to later in the day because of Amber. Because she has class. Vicky will follow up by email to let people know sort of what that looks like.
Hmm.
Possibly in some kind of survey version, but it looks like we'll probably keep Wednesdays, just around noon or so.